Hi everybody. Today we know the value of pi is around 3.14. Some of you may go more precise, some of you may go less precise, but it's around that number. Now let's take a step back for a moment though. How do we arrive at this value for pi? The answer to this is rooted in thousands of years of history where for a really long time we have been trying to figure out what the value of pi is via a bunch of clever and cutting edge techniques, definitely for the time these techniques were used in. And so what we're going to do is look at some of these techniques and implement them ourselves and calculate the value of pi on our own machines using JavaScript. It's going to be a lot of fun. So let's get started. Originally, the way we calculated pi was by taking a circle and measuring two things. The first thing is known as the circumference, which is just the distance around the circle. The second thing is known as the diameter, which is the distance across the center of the circle. So if it visualizes, it looks a little bit like this. And many of you who may have taken basic geometry in school many years ago, this all should be very familiar to you. And if you haven't, it's okay. The main thing to note is that the circumference is, the round shape all the way around. If you walk around the circle, what is the distance for that? And the diameter is if you take a shortcut and walk right to the center of the circle, what is the distance for that? And now what many people found is that there's a common pattern between the circumference and the diameter. That is, no matter how big the circle is or how small the circle is, when you divide the circumference by the diameter, the ratio between the both of them, there's a constant value that basically doesn't change. And that constant value eventually became known as pi, and the value for pi has often been as precise as how well you could measure between the circumference and the diameter. So it might have started off at something more basic like just 3, but as measurements became more accurate, you got 3.1, 3.14, and so on. And the interesting thing is that as we've gotten better and more precise at measuring pi, it took a lot of time to really make major jumps in how precise we were. And you can see this following visualization from Google's blog post on this exact topic. You can see that, many years ago, we had 3.16 and 3.125, and for thousands of years, it pretty much stayed within that range. And then Archimedes came and had a range, and we'll talk about Archimedes' approach in a little bit. And then it stayed mostly, more precise, but didn't make any major jumps until we got more advanced mathematical techniques like the infinite series in the 1400s all the way up to almost the mid 1900s. And then once the computer came along, you got to see massive jumps in how precise we became. We'll look at some of the infinite series mathematical approaches in what we're going to be doing as well. So a lot of fun stuff to cover, both in terms of how people did it back in the day, but also how we can turn some of those techniques into JavaScript that we're going to be using. So what we're going to be finding out is we're going to take a few popular approaches, and it's going to really just combine some more basic JavaScript concepts around functions and looping, console logging, and mathematical operators. I know this seems like a really complicated topic, but as you'll find out, a lot of the complexity really is in the classic challenge of translating what we're seeing in terms of a problem, or in this case, a mathematical equation, into terminology and a format that our computer can understand, or more accurately, our computer can understand when represented in JavaScript. So, but before we go too far though, if you're watching this video and your goal is just to, I just need to use math.pi, or I just need to calculate pi for something I'm doing, there is an easier approach. You don't have to reinvent the wheel here. Math.pi is a global constant on the math object. So anywhere in your code, just type in math.pi and you will get a value of pi, which is as accurate as we can get using the number of digits we can have in JavaScript. So if you're here just to get that value, you can pause the video and be on your merry way and just use math.pi. But I do insist though, even if you came here just for math.pi, what we're going to be seeing in the next few minutes is going to be pretty exciting and a lot of fun in my opinion as well. So we'll cover those things also. So let's go back and look at one of the more early approaches that got pi fairly accurately, and that was by Archimedes. And so what we found out, and Archimedes actually found out, is really that measuring the circumference of a circle was tricky. You needed to get a very precise ruler, a precise measuring instrument, and you're going around a circular shape, which is not exactly easy as well. But what if you could kind of, approximate the distance around the circle, the circumference, by measuring a perimeter of a shape with straight lines, like a polygon. Like what if we did something like this? You know, measuring the circumference, tricky, but measuring straight lines around a shape like this 5-sided pentagon is much, much easier. And so what Archimedes did is, let's just cake a circle and wrap it with polygons both on the inside and the outside. And what this would create is almost like a little wrapping where the outside polygon's perimeter would be the upper bound of our circle's circumference, and the inner polygon's perimeter would be the lower bound of a circle's circumference. Now, that might be hard to visualize, but that's how we have a visual. So in this case, for example, notice that we still have a circle, but instead inside of a circle, we have a 5-sided polygon. On the outside, we also have a 5-sided polygon that wraps it. And similarly, we go to 6 sides and 7 sides. And as you can see, as the number of polygons we keep adding increases, the more accurate the gap between what we're measuring to the circle and discarded space gets less and less. Here you can see a lot of wasted space, but here you can see much less space, which means we're getting closer to being able to approximate the shape of a circle using nothing more than straight lines. And then what basically ended up happening is that Archimedes, 96 sides later, I don't even know what a 96-sided polygon is even called, he was able to come up with this approximation, which stood the test of time for a very long time. That is that pi falls in between 223 divided by 71 on the lower end, and then 22/7 on the higher end. So pi is somewhere between this range. Now, a part of this activity is not just to know about how what people did back then to calculate the value of pi, is actually do this ourselves in JavaScript. And so for this one, I'm going to quickly go into VS Code. I have a very simple page here, nothing too crazy going on. It's blank HTML, there's a script element, and then we have function calculate pi. And in this case, I just have the exact code or the exact version of Archimedes' equation between the lower and upper bound represented here. So you can see lower is 223 divided by 71, and upper is 22 divided by 7. In this case, the translation was taking the division operator, which is the slash, and just representing it with a variable. And then I have 3 console.log statements. One is that captures the lower value, the value of math.py itself, which is the actual value of pi that we currently have stored in JavaScript, and then the value of upper, which is the upper bound. And you can see that when I run this page and open the console, you can see the value showing up here. You can see that 223 divided by 71 gives you something like 3.14, and then 0.84, which is slightly less than the 3.14159, which is the value that we're all more familiar, which is the accurate value from math.py itself. And then you have the upper bound of 3.142. But if you just take a look at this value though, between the lower bound and the upper bound that Archimedes came up with, it's reasonably accurate, at least if you look at the first 3 digits. And I'm sure if you average these 2 values up, you get closer to 3.159 than you would have using approaches that at that time were typically used. And so that's the approach of using the polygon approximation way. Now let's jump forward a few thousand years. The numbers and mathematics, huge leaps in how people understood and started working with them. The ability for us to calculate the value of pi really accurately also grew accordingly. So as we got better at representing numbers, understood number theory, and went really deep in various mathematical techniques, there's a lot of things that we could do that we couldn't do before, but one of those things is applying it to solving what is the value of pi. And one technique from the 16th and 17th centuries that helped here is the application of what is known as an infinite series, those techniques towards figuring out the value of pi. And the general idea of infinite series is that you have a summation and you have an infinite number of calculations that as you go down calculating something over an infinite period of time or infinite iterations, you converge on a single value. So if you're starting off very early, you have like a few calculations, you're going to be slightly off base. But the more calculations you do and the more you sum those values up, you're going to rally around a common value, which in this case is the value of pi. There are many infinite series formulas out there, many ways of solving for various different things. But in this particular one, there's an approach that allows us to converge onto the value of pi. So eventually get to the point where the more calculations you do, the amount of accuracy you get is not quite as large, which is why it basically becomes a straight line in terms of convergence, whereas early on you can see it's wildly off base until you get to more accurate numbers. And the approach that was really popular here is the Gregory-Liebniz series, which came out in 1676. And here's the approximation of what this equation looks like. You can see the value of pi equals 4. This sigma character, which defines in this case an infinite series where you start from 0 and you go an infinite number of times, and then you calculate the actual summation. Like, what do you calculate an infinite number of times? It is this equation right here. Now, when you look at this, right, this might look a little scary. It might be those things you might see in like movies, like, you know, those mathematical type movies that have like, you know, all kinds of equations on a whiteboard that you need to make sense of. But in this case, what we're really saying here is that you have this thing, you know, -1 to the power of n, and the whole thing divided by 2n plus 1. And we're going to start from value of 0, and then 1, and then 2, and then keep adding those values up, which in our world really means is that the sigma operator, which defines this summation property of infinite series, is nothing more than a for loop. You know, we start with 0, and now in the mathematical equation, they're expected to go up to 1,000. The idea of 1,000, or sorry, expected to go up to infinity. In JavaScript with computers, running something an infinite number of times, never a good idea. So we're going to start with a large number and just say 1,000, just to keep it a little bit simple. And what gets summed up is this equation right here. And so you put it all together, we need to look into what it looks like in JavaScript. And so the way I'm going to do this is by, let me go back to our code editor, and let me go and translate that entire function into something that makes it easier for us to represent. And so instead of writing all this code ourselves right now, I'm just going to go and paste some code in and then walk through exactly what this looks like, because that's going to be a lot more, you know, sensible and a good use of your time as well. And so I'm going to go ahead and paste this all in. You can now see that we have a function called calculate pi. So that has not changed at all. And the thing is, we have the for loop, which we talked about earlier. And then in the numerator, we have math.pow equals -1 to the power of n, which is part of the equation we saw earlier. And then in the denominator, we're just dividing by 2 times n and then plus 1, just doing the simple division between those things. And because it's an iteration, we're storing the value of each calculation as part of our loop in this total value. And notice I'm using plus and equals to make sense of what's going on here. It's not just equals, it's plus and equals, because with each iteration, we're incrementing the value of total, which hopefully over a period of time will slowly start to equate to the value of pi. And you can see the final value equals 4 times total, which is really just, when you look at the equation, we're multiplying that by total. Let me go back to our equation here. You can see that, you know, we have 4, and then we multiply the equivalent, the result from the for loop by that value that we see right here. And so let me go back to our Visual Studio Code, and now all we really need is just the console log statements to make sense of what exactly is going on. And to save you some time here, I'm just going to copy and paste that in as a result as well. And so console.log, and notice what we're seeing here. The value of pi we calculated is, you know, final, which is the value we have here. The value of math.pi is math.pi, just like before. We're making sure we still have our original source of truth visible, so you can kind of compare how it's doing. And then I'm also storing the difference. You know, what is the difference between what we calculated and what the actual value of math.pi is? And so let's go and run this code. And when we run this, you can see the value of pi we calculate is 3.14059, and the value of math.pi is 3.14159. So you can see there's a slightly big gap here, and you can see the difference is like 0.000999. You know, it's pretty small, but it's still sizable though, because we kind of talked about, you know, we talked up infinite series and how awesome it is in being able to converge on the value, but this is not really a great number. And so what we can do with infinite series, or in any situation where we need to get a value but it's not getting accurate, is increase the number of iterations. So here we're running for 1,000 iterations. Let's make it 1,000,000. Let's go ahead and make it 1,000,000 iterations and refresh the example. And once we've done that, notice this time the value of pi we calculated is 3.14159, and you know, it gets a little bit off from what we had originally, where it becomes a 165 instead of a 265. But you can also see that the difference now becomes very, very small. And if I were to add a few more zeros, like, I don't know if it's going to work, but let's find out. Refresh this page, it's running. You can now see that we're almost as accurate as the value of pi is. We're just running it many more iterations. Now, as you can guess, there's a challenge here. The more iterations we run, the more accurate our results are, as we saw here. But you also saw that when I ran it, there's a pretty sizable lag between calculating the value of pi and then the application being responsive. And so it's a balance that you typically need to strike between an infinite series calculation where do I want accuracy or do I want speed? But there is another option here. There is another way of thinking about this, which is what if there's a better calculation we can do that allows us to get a more accurate value without running something, many millions and millions of times. And that special something is another technique that was, in the same vein of infinite series, which is the Bailey-Borwein-Plouffe example or formula, also known as BBP, which is one of the more faster and more popular approaches for calculating pi if you really need to calculate it yourselves. Now, this equation looks a whole lot more complex than we had before, but this is where the looks in many ways are more deceiving than they're not, because what we're really doing here is, again, we are doing a summation, and then we're just summing up the calculation for these values that are inside of it, which is 1 over the power of 16n, 1 divided by 16 to the power of n, and then all of that, it's a scale value essentially, multiplying it all through just 4 fractions that we're just subtracting. 4 over 8n plus 1, minus 2 over 8n plus 4, minus 1 over 8n plus 5, and minus 1 over 8n plus 6. So just more things for to translate into JavaScript, but the techniques itself in terms of how do we go from turning to the for loop and doing the numerator-denominator multiplication and to the power and fractions, all those basic mathematical operations, they still hold true. Now, one way you can simplify these things is by looking at it in terms of 2 sections. The for loop, that's non-negotiable. We have the for loop, it's going to run. But inside of it, we can break up our calculation into section 1, which is the inner part of the calculations, and section 2, which is the outer part of the calculation, which is another way of thinking about it, where in the previous example for the version we saw earlier, where we had to kind of figure out in the Leibniz and Gregory-Liebniz series, we essentially separated by numerator and denominator. Here we're separating it by 2 sections. And if we look at the code for this one, let's go ahead and see what this is going to look like. It's going to be a little different, but not too different in the grand scheme of things. And so I'm going to go ahead and paste the value for this one right here, just so you can see it more easily. And and in this case, notice that we still have our for loop. Nothing changes on that front. And we have it running, in this case, just for 100 iterations. So not 1,000, not multiple millions. And then we have the scale, which is the outer function, outer calculation we're doing, which is 1 divided by math.pow, 16 to the power of n. And then we have the inner calculation, which is a lot of fractions that we need to turn into an equation. And then the iteration, which is the calculation at each run of our for loop, it's just scale times timer, which we're then, or scale times inner, which we're then incrementally adding to the final value. And then we just have our console log statements again, which allows us to see what value we calculated, the value of pi, and the difference between them. So let me go ahead and hit refresh. And notice that the result came by very, very quickly. And the answer that we came up with from this calculation is actually the exact value that we get when we do math.pi. So the difference is 0. And the other part is we only ran this 100 times. So it wasn't even run for many iterations, which makes this calculation almost instantaneous. Just for kicks, let's run it 10 times and see if we get close to an answer. Well, yeah, I mean, even running it just 10 times, we get an answer that is much, much closer to the value of pi than we would have gotten with the earlier Gregory-Liebniz approach, where we even had like 1,000,000 iterations run. So, what if we just run it 2 times? Yeah, when you run it 2 times, you can see the answer is a little bit off, but still though, that is pretty impressive when we had to compare it earlier to tens of millions of iterations to just around 100. We get a very, very accurate result, almost nearly instantaneously. And of course, we did not stop there with infinite series. As you saw from the chart earlier, there have been many more advancements in how precise we got in calculating pi. The introduction of computers and supercomputers and cloud computing, all these things really upped the game in how accurately we can calculate pi, all the way up to where we are right now, which is 100 trillion digits of pi, which is recently calculated by Google as part of some experiments they were doing on the cloud and just pushing the limits of how far they can take computing. And so I'm sure by the time you're watching this video right now, this number would have been made much, much higher by another more clever solution. So there you have it, an overview of just how pi became pi, how did it go from essentially being a constant that we kind of measured by taking the ratio of the circumference and the diameter to getting really more precise and finding not just geometric techniques like Archimedes did to more advanced mathematical approaches using the infinite series technique that I showed in terms of both the Gregory-Liebniz approach as well as BBP. And there are countless other mathematical approaches, both in the trigonometric realm and in the polar realm, that have all contributed to helping calculate pi, all the way up to the most recent one, which is the 100 trillion digits of pi that Google calculated, which is the Chudnovsky algorithm. So a lot of links there. I have linked to the blog post from Google that goes into detail on some of these activities. And there's an article I wrote about this as well, which is also linked in the description of the video. And so with that, if you have any questions about pi or anything related to just running cool JavaScript experiments from mathematics and equations into something you see on the screen, post in the forums at forum.crypto.com, where I and others would be happy to help you out. If you enjoyed this video or didn't enjoy this video, that's okay. Still, tell your friends and enemies all about it. Hit subscribe to be notified of new videos I'll be making. Follow me at Krupa on Twitter and Facebook and Pinterest and all sorts of places where I happen to be posting web development related things. Join the newsletter. There are a few 100,000 people who are actively consuming some of this content in email form that I post regularly. So feel free to sign up, link at the bottom. And lastly, if you like the style of my explanations and presentation, you might like some of the books I've written on a variety of topics, front end and non-front end related. And so check, if you don't like the books in their paperback editions, they're also Kindle forms. So you have an edition in a format that hopefully you and anyone else will find really useful. And with that, I will see you all next time.